our objectives for today is that you will be able to recognize and describe projectile motion. So we're going to talk about what projectile motion looks like, and so if you're given a situation, you'll be able to determine if that is or is not projectile motion. And then when we do have situations that have projectile motion, you're going to be able to resolve that projectile motion into its components and then apply the kinematics equations from the previous chapter to solve problems where projectile motion is an issue. Projectile motion. Before we begin, I want you to think back to the kinematic equations from the previous chapter. So I'm just going to put them up here as a refreshment to your mind because we're going to look at some equations today connected to this, and I want them to be fresh in your mind. Okay, so we have solving for displacement and for velocity final using a variety of different methods. And then these can all be manipulated to solve for acceleration or for time or for velocity initial. Okay? All right. We could, if we wanted to, rewrite all of those equations that we just looked at to work for vectors in 2 dimensions. Okay? We could do that. It would be a mess. Okay? Because when objects are not propelled either straight up or down or in a straight line, okay, their acceleration, their displacement, and their velocity are all pointing in different directions. Which means that the equations that we would write would be very complicated and difficult to use. In order to make this process easier, instead of trying to write equations that would work with a resultant vector, we can instead break that resultant vector down into its components. So we can use the skills that we have already learned to resolve that vector into its horizontal and vertical components. And then we can use the equations we used in the previous chapter for one-dimensional motion on those components. And when we have done so, we can then use the resultant component or the components that we get at the end and recombine them to get our new resultant, rather than trying to put the resultant through the equation. So, let's take a look at what this might look like. Okay? A projectile is the motion of an object that is either thrown or launched or sometimes falls into the air. Okay? Projectiles travel in parabolic paths. So if you have been in math, you know what a parabola is. It looks like this. Woo. Okay? So if you throw a ball or launch a rocket, or if an object falls off a table, it's going to have a parabolic path. Okay? Now, is it always going to be the entirety of this parabola? No, not always. Okay? So if I have a table and I knock a ball that's rolling off of it, the ball's going to fall kind of like this. So I'm going to get only one side of the parabola, right? It's still projectile, just a different portion of the parabolic motion. But it's always going to travel in a parabola. And it's important to note, okay, that if you're measuring the velocity of an object, like if the velocity vector is your resultant vector, that at the top of this point right here, at the top of the parabola, your y value for velocity would be 0. Because remember from when we talked about free fall, when an object reaches the peak of its motion, then it temporarily stops moving, right? So for this one, its y acceleration, or its y velocity would be 0. Now it's obviously still moving because it has an x value going in this direction. Okay? Projectile motion can be resolved into horizontal and vertical components. And then the kinematics equations from chapter 2 can be applied to them individually. This is what those equations could look like. Okay? So you can take those kinematic equations and apply them just to the equations. And now these equations that we're looking at right now are for when the vertical motion of the projectile falls from rest. So we're talking about falling projectiles. So you'll notice that in the velocity y final equation, they've removed the velocity initial because we're assuming it's falling from rest. So that's why they've removed velocity initial from some of these equations. But really all they've done is taken and changed it from saying velocity final to the y velocity final, and from just plain velocity to velocity of the x direction. And what they want you to understand is that at least for this horizontal motion of a projectile, your initial velocity that they give you is going to be constant. So we're assuming that horizontal velocity doesn't change. We're ignoring the potential of friction, essentially, is what they're saying. We're taking our fun little physics world and putting it in a box and removing some of the factors to simplify this process for ourselves. And the factor that we're removing here is friction or air resistance. We're saying so long as the projectile is in motion, its velocity x is going to be constant, which means we're going to use the equation for constant velocity or for average velocity that we used from the previous chapter. So that's the velocity average is equal to distance divided by time. And then in this image, they've manipulated it to be solving for distance. Okay? It's all well and good to have a bunch of equations, but it would be nice if we could use them, right? And see them in action. That might help us. Projectile motion can be thought of as free fall with an initial horizontal velocity. Because remember that free fall is just when you have an object in the air and the only acceleration on it is the force of gravity. Okay. Well, once you launch the projectile, it continues to have that initial horizontal velocity, but then once again, it's in free fall. The only thing affecting it aside from that velocity is now the force of gravity. So again, we have a free fall situation here. Because horizontal motion is independent of vertical motion, if one ball is dropped and another is fired horizontally from the same height, they're going to reach the ground at the same time, which is a little counterintuitive to our brains. What we're going to wind up with is something like this. So imagine you drop your ball from a certain height, and the force of gravity pulls it downwards. Okay. If you fire another one this direction, the horizontal velocity with which you have fired it is not going to affect how strongly gravity pulls on it. So it's going to fall down at the same rate that it would if it had no horizontal force on it. All the horizontal force is going to do is at the same time that it's going down, it's going to go a little bit in the direction of that horizontal force. So you'll wind up with the ball falling at the same rate and hitting the ground at the same time, but instead of falling straight down, you'll get that parabolic motion.
Is this the same as the...
To find the velocity of a projectile at any point in its flight, you can find the vector that has the known components, then use Pythagorean theorem to find the magnitude of the velocity. And then you can use the tangent function to find the direction of the velocity. So you will be figuring out which components you do know and then using those vectors to come up with your resultant. So let's apply that. Okay. Example problem says the Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose you kicked a rock horizontally off of that bridge. The magnitude of the rock's horizontal displacement is 45 meters. Find the speed at which the rock was kicked. Here's what we know. We know delta y, and we know delta x, and we know the acceleration of y because it's the acceleration due to gravity. What we're trying to solve for is that initial velocity, which we know is going to be constant and the same as our x value for velocity. Okay? I'm going to give you a minute. I want you to see, try it maybe, and then we will see if we can do it together as a group. Where would you recommend beginning? Well, we're solving for Vx. Do we have any equations that include Vx? Okay, so we have one equation from the previous one, which was, oh, didn't mean to move ahead, meant to write on it. There we go. The one that we said was for constant or average velocity, which they had manipulated to solve for displacement. However, what is the problem with this equation? Right, we don't have a time value. So we're going to need another equation. And the equation that we're going to select should probably have time in it so that we can isolate time and substitute in some values for time that we do have, correct? So, the last y one is, in fact, the one that I would recommend. So the last one from the previous page that has delta y equaling 1/2 of acceleration y times time squared. Okay, so we should then be able to resolve this equation to get time by itself. Okay. And when we do that, what we're going to wind up with, I will spare you the trouble of manipulating it on your own, is you're going to wind up with time equaling the square root of 2 delta y over acceleration of y. Okay. So now we can take this value that we have for time, because we have an acceleration and we have a delta y, correct? And we can plug that in place of time in our original equation, isolate for velocity x, and solve. So if I'm going to just wipe my screen here real quick. If we take our equation, we have Vx is equal to change in distance over change in time. And instead of time, we can plug in we'll do the inverse of our thing so that we don't have to make a weird messy fraction, and do the square root of ay over 2 delta y times delta x, and then we can go ahead and solve. So now all we have to do is plug in values. So our velocity x should be equal to the square root of negative 9.81 meters per second squared divided by 2 times negative 321 meters, and then take that whole thing times 45.0 meters. If we work out the math on this, we come up with roughly 5.56 meters per second as our velocity. Okay, let's try one where you guys try it. Okay, we're gonna do one from the book. We'll do baseball, rolls off a desk, and the desk we're gonna say is 0.07 0.70 meters tall, and hits the ground 0.25 meters away. And we want to know how fast was it rolling. So you're going to wind up using the same equation we did for the previous one and just plugging in your new values. And if you calculate it out, you should come out to 0.66 meters per second. Does anybody need to see that run? Okay. Then we're going to try just one more that's just slightly different. Okay. So Pelican travels 7.6 meters per second to the right. .7 meters above water. If it drops a fish, how far horizontally will it travel before it hits the water? Okay, we're gonna erase my terrible handwriting and draw a picture instead. So we have our little birdie. He's dropping a fish. This fish we know is gonna travel in a nice parabola down until it hits the water. Okay, we know that this distance is 2.7 meters, which is negative because it's moving down. And we know that the bird is currently traveling, so our velocity x is equal to 7.6 meters per second. Okay. And what we want to know is this distance right here. What's that going to be? Okay. So if you look back up above, you'll remember we had delta x equals vx times delta t. And we solved for delta t previously, so we know that delta x is going to be equal to 7.6, which our should be squared. No. Not squared. My bad. Delta x is going to be this value times that whole big conglomerate that we came up with. So the square root of 2 times the change in y, which we know to be negative 2.7 meters, all divided by acceleration due to gravity. And the result comes out to be about 5.6 meters. All right, we're going to stop there. We'll do the other half of these on Monday. Enjoy your long weekend.
Do you want this or do you want me to plug this?